In this video, we'll look at things like specific heat, the Carnot cycle, entropy, and the laws of thermodynamics. Well, let's get started. If I want to find the specific heat of a metal, I can heat up the metal to temperature 1, maybe in a hot water bath somewhere. And then I could drop that into a sample of water here. And again, we need to know the beginning temperature of the water and the amount of the water. And we'll just let it sit in there until it becomes in thermal equilibrium. So temperature 1 is the temperature of the metal. Temperature 2 is the beginning temperature of the water. Temperature 3 would be the final temperature of the water and the metal. So we're going to use the concept that the heat flow, Q, of the metal is going to be equal to the heat flow, Q, of the calorimeter. We'll call this beaker full of water the calorimeter here. Now we'll put a minus sign here for the metal because it's losing energy or losing heat, and the calorimeter is gaining heat. So then we'll do the equation, for specific heat and energy. Q is equal to specific heat multiplied by mass multiplied by temperature 2 minus temperature 1. So let's do it for the metal. So the metal is going to be minus whatever the specific heat is multiplied by the mass of the metal multiplied by T3 minus T1. And that's going to equal water, which the specific heat is 4.184. So we know that one. Multiplied by whatever mass of the water you have, and then multiplied by T3 minus T2. And then we know all of this, we know all of these, we know mass of the metal, you want to measure that, then you can just find the specific heat of the metal. So that's pretty simple to do. Okay, now what about the Carnot cycle? Okay, remember the Carnot cycle is a theoretical construct for the most efficient heat engine that we can have. We will start at position 1, and then we'll curve to position 2, down to 3, back up to 4, and back up to 1. And we can get our temperature here. This one's actually temperature hot. And this one down here is temperature cold. And we get that using the Pivnert equation. PV is equal to nRT. You'd be given the pressure and volumes and number of moles. R, of course, is the 8.31 gas constant. And you can find temperature at this position. That would be your temperature hot. And this would be your temperature cold. Remember, our efficiency is temperature hot minus temperature cold divided by temperature hot. And then that would be then multiplied by 100 to get it into a percent. That was on a previous video. Okay, so what's the process with this? The first one is an isothermal expansion as the gas expands against an outwards atmosphere, or we should say an external atmosphere. So isothermal means that the temperature will not change. Okay, so temperature does not change when you have that. So let's look at our equation here. We know that delta U, the change in internal energy, has to equal heat flow Q plus work done. And change in internal energy only depends on temperature change. So if temperature does not change, then 0 is our change in internal energy. Okay, we're going to have heat flow in. So Q is going to be a positive Q here. And then whatever work done by the expansion of this gas is going to be negative for the gas. Now again, we're looking at the system here, not the surroundings. It's negative for the system of the gas. So that'll be minus W. And we can conclude then that the absolute value of Q must equal the absolute value of W. So I'll put little absolute value signs on this. So all the heat flow coming in, okay, is going into the pressure volume work that the gas is doing. Okay, now the next part here, we have another expansion. This is called Isentropic. Now, we called this adiabatic in class. Okay, isentropic means equal amounts of entropy, so there's not going to be any real entropy change here. So, but you can call it adiabatic here. Now, what that means is heat flow is equal to 0. Okay, so we're not allowing any heat to exchange or mass and friction. This is a frictionless, reversible situation where no heat flows and no mass exchange between the system and the surrounding. And that's why it's called isentropic. It's adiabatic, which means no heat flow. Okay, so if heat flow is equal to 0 then, so we have delta U, okay, is equal to, Q plus W again. Okay, so delta U, the change in internal energy, then has to be equivalent to whatever work is being done, okay, by the gas, and that's going to be a negative. Okay, therefore delta U will be negative, and we expect temperature then to drop to temperature cold in that condition. Okay, so that's why we get a really rapid drop in temperature, because all of the work of the gas happening at this stage, okay, is coming from the internal energy of the actual gas. Therefore, its temperature has to drop. Okay, now on the way back from 3 to 4, we're going to make our way back up to T hot here. We have an isothermal compression here. Now remember, isothermal does mean delta U is equal to 0 again, so we'll have 0 this time equals, now heat's got to come out, so a minus Q, and this time it's going to be plus W. From the perspective of the gas, work is actually going into the gas now, okay, because it's being compressed. In the first half of the cycle, work is going out of the gas. It's expanding against an external pressure, so therefore work is negative. So, and again, in order to allow delta U to be equal to 0, the absolute value of Q has to equal the absolute value of W. And then finally, another isentropic, okay, compression here, which again means adiabatic. So Q is equal to 0 again. So that means delta U is going to equal W, because again the Q value would here would not exist anymore. It would be 0. Except now it's a positive in both cases. Why? Because work is going into the gas, and its internal energy must increase because work is being done, and heat flow is not allowed to exchange here, so no heat can come out of this. So as it compresses, it will then go back up to temperature hot. Okay, and again, this is a mental construct of the most efficient heat engine you can have. Remember, the lower you can get T cold, the more efficient it should be. The most efficient heat engine then would be T cold equal to 0 Kelvin. And of course, we know that does not exist in real life.